This example is all about flocculation. We're going to design something that looks like this picture here, and we're looking at the Chapter 3A, Coagulation and Flocculation PowerPoint slides here. And this is really where the example problem is defined. A cross-flow horizontal shaft paddle wheel flocculation basin. And the flows are given, the GT values are given to us. They talk about tapered flocculation is to be provided. And we have an average G value, etc., all the way down. So let's dive in. Actually, why don't we look first at what this actually looks like from a satellite view. This is the Whitty-Atkins water treatment plant, and the flocculation basins are here and here. This plant is a mirror image plant. So let's just zoom in on one side of this mirror image. This is as close as I can take you in the Google satellite view, but notice we've got 1, 2, 3 compartments on this right side, and the same thing is on the left side too. But we have several paddles here. These are the flocculation paddles. This is the chamber that we're designing. The plant was designed the same way as this example problem. So let's look back at this example, and what we're asked to do is determine the GT value, basin dimensions, all the way down. So there's 7 items here, I believe, and I've already worked this out and provided to you this PDF, but I'm going to walk you through the PDF and explain what it is that we're doing. So let's zoom on in. Flocculation example. This is the side view of those paddles. Remember, they're very long, stretching, in length or width, however you look at it. But the side view looks like this. And the first bullet point we needed to calculate was the GT value. GT value is simply the velocity gradient that's given to us times the residence time, and we do a unit conversion, 60 seconds per minute, and we get 72,090, and this is a unitless number because G is reciprocal seconds, T is seconds, and so we get a unitless value. This is between 50,000 and 100,000, so we're okay. Let's take a look real quick and see, where did these numbers come from? 26.7 seconds. Let's maybe look up here. 26.7, the average G value was given there. And 45 minutes, I believe the retention time of 45 minutes was given. Yes, they call it detention time, same as retention time of 45 minutes, and that's how we can calculate our GT value. On to step 2, the basin dimensions. We were told 25,000 meters cubed per day of flow. So if we know we've got 25,000 meters cubed per day of flow, and we know that our detention time is 45 minutes, we can convert from meters cubed per day to meters cubed per minute, multiply times the 45, and our volume is 781 meters cubed. That's pretty straightforward, actually. We'll zoom out a little bit and see now that we have this. This is what the flocculation basins look like from the top view. The lines are a little faded here in this scanned-in image. So let me turn on my pencil where I can highlight what this should look like all the way through, something like that. My lines are not straight, but that's what we're talking about. So if the total volume is this 781 meters cubed, and we were told in the problem statement again that the width is going to be 15 meters, then what that means is 781 divided by 15 is going to give us our side view area. So this total area right here must be 52 meters squared. Now you may remember at the very beginning we defined these things as x, x, and 3x. So we're assuming we have a square side view for each compartment, and so that means it must be 3x wide total. So coming to the top up here, 3x times x must be the 52 meters squared that we just saw in the side view area, and we solve for x and we get 4.16 meters. So the height, this x here, is the 4.16 meters, and this is the height of the water, by the way. We would have to add a little more on top, and that's what we call freeboard, but we're interested first in just finding out how tall the water is. The length is going to be 12.5 meters, and that's this length here, and the width is that other width that we saw in the plan view, and it was 15 meters. Okay, so now we know the size of each compartment. And part 3 was the paddle wheel design. We're going to use the design in slide 44. So let's take a look at that. Slide 44 shows us a paddle wheel design where we have 3 paddles on each arm. Well, there's 2 arms, but 3 paddles on each side. And so 6 paddles total, and this is essentially the side view of the paddle. Notice we've got a motor. This would be a chain that's turning this shaft. The shaft is going through all of these, and so we have this one paddle here. And notice the dimensions. We define D1 as the diameter of the outside paddle, the center to center diameter. That's important, actually. D2 is the diameter of the middle paddle, and D3 is the diameter from paddle to paddle of the inner paddle. Okay, I think those are the key dimensions that we need to pay attention to. And we can see that from slide 44, we're just going to go ahead and choose D1 to be 3 meters, D2 will be 2 meters, and D3 will be 1 meter. And the idea is that we simply choose these, and then we do all our calculations, and we find out if the design is within specs, and if it is, then we're good. If not, then we can adjust these diameters to give us the right performance. The blade width is 0.15 meters. I don't know if that was given in the problem, but that's sort of a typical blade width. And the blade length is 3 meters. Again, that's a typical blade length. And again, if our design didn't quite work out, we could adjust these. 6 blades per paddle wheel. 6 blades per paddle wheel is what I just mentioned on the other slide, and 4 paddle wheels per shaft. What this means, again, if we're looking at the top view, we've got these 3 compartments. We're going to have 1, 2, 3, 4 paddle wheels per shaft, and I've drawn what one of those paddle wheels looks like in a little more detail here. So there we see our 6 blades. 3 meter width is given there, and again, each of these paddles is going to be the 1.5 meters wide, so 15 centimeters wide. Okay, so from that, we know the blade area per shaft is 0.15 times 3 meters times 6 paddles per wheel times 4 wheels per shaft, and the total blade area per shaft is 10.8 meters squared. So what that's saying is each of these shafts, so 1 shaft, 2 shaft, 3 shaft, each of those has a total of 10.8 meters squared of blades on it. Then the cross-sectional area of the water flow is 15 meters wide by 4.16 meters high. And what was that? This was the width of 15 meters by the 4.16 meters. Essentially what we're saying in this is we want to figure out how much area the water is flowing. So water is flowing in this direction. That's part of what might not be super intuitive about this drawing. But the water is flowing from left to right, and so it enters each compartment through a baffled wall, a wall with holes in it or slats in it. And so it's this area that we need to calculate as the flow is moving from left to right. So that cross-sectional area is this 15 meters by 4.16 meters, and we get 62.5. And then we want to calculate the percent cross-sectional area of our paddles. We just figured out that our paddles are 10.8 meters squared, like the total blade area per shaft is that. And then we just figured out our cross-sectional area is 62.5 meters, so the percent area is 17%. And this is good. We could look in some of the standards and some of the typical designs and see that you don't want too much blade area per shaft. You don't want too little blade area per shaft either. But if you have too much blade area per shaft, water is not going to be able to flow through the paddles, and we would get this big circular flow. In other words, when we go back up here, we are going to get some circular flow of water as this paddle travels around, but we don't want too much. In other words, we wouldn't want a paddle that is totally solid, that's just pushing the water around. We want the water to go through the the paddles to move through the water, and that is what we can assure by making sure that our cross-sectional area, our percent cross-sectional area, is somewhat low. Okay, the fourth step, we need to figure out what the power imparted in each compartment is, and we use this equation 3.12, which is our G value. Same thing we used for a rapid mix tank. And we know our viscosity because they gave us our temperature. We know our volume because we just calculated it, or actually we need to pay attention to that. 781 meters cubed. We're dividing that by 3 because we have 3 compartments. So our total volume is 260.4 meters cubed, or I'm sorry, our volume per compartment is 260.4 meters cubed. And that's important because we are designing sort of each compartment separately as we go through this design. And the G values were given to us, 50, 20, and 10. This is what we call tapered flocculation. Why do we have tapered flocculation? Because we need good mixing at the beginning, so we add a little more power. But as we begin to form flocks, we don't want to break up those flocks. So we have sort of a less intense mixing in the middle compartment, and then a more gentle mixing in the final compartment, so that we still get some flocculate. We're still mixing the water to some degree, but we're not going to break those flocks up if we go with a lower G value. In compartment 1 then, we can calculate that the P, the power imparted to the water, by solving this equation. We're going to calculate that this was G then, this is our viscosity, and this is our volume of that compartment, and we calculate that our power is 851 watts. You need to prove to yourself that per second times Pascal seconds times meter cubed with the squared per second does give you watts. Make sure you understand that. We do the same calculations for compartment 2 and we get 136, and for compartment 3 we get 34. Now, part 5 was rotational speed. We know that we need this much power calculated above, so how much rotational speed does that require? And for that we use equation 3.19. Now this is the place where design of these flocculation paddles is different than the flocculation tank that was similar to a rapid mix tank. We didn't use an empirical equation, or we did use an empirical equation in that calculation, but here it's not really an empirical equation, it's more of a fluid dynamics equation where power is the coefficient of drag times the area of the paddle times the density of water times the velocity of the paddle cubed divided by 2. And notice that the total power here is going to be affected by the 3 different types of paddle that we have. In other words, paddle 1, that outer paddle, is going to be traveling faster than paddle 2, and which will be traveling faster than paddle 3. And we can kind of see that, actually we can see that in this design. As this thing rotates, we know that the things that are traveling on the outside of the wheel are going to rotate faster than the things that are traveling on the inside of the wheel. So we need to break this into 3 parts of this equation. CDAP rho over 2 is common in all 3 terms, so we can pull that out here at the beginning, and then it just becomes the velocity of paddle 1 cubed plus the velocity of paddle 2 cubed, velocity of paddle 3 cubed. Now what is the velocity? We can write it this way, K pi in D1. And actually, this just goes from a geometrical consideration here. If we want to know the speed of a paddle, all we have to do is multiply its rotational velocity times the circumference of the circle that it's traveling. And the circumference is pi times the diameter. So, for example, if I had a 1 meter diameter circle, then pi times the diameter would be 3.14. That would be, the circle is traveling a distance of 3 meters, 3.14 meters around. So that's the distance, and with the angular velocity, sort of the number of rotations per time, then I can calculate, how fast is this thing traveling in kind of a meters per second speed term. Now the only caveat here is that we have K. What is K? The issue is that even though because the paddles are traveling in this direction, we are going to get some water flow in that direction too. And as the water flow is moving in that direction, the flowing water is not going to feel the paddle at the same speed that we calculate. So we have to adjust for that, and this was given to us in the problem, and it is saying that the speed of the blades relative to the water is 75% of the peripheral blade speed. That's where this K comes into play. K is going to be 0.75 because the water only feels 75% of the actual speed of the blade. I know I just told you a minute ago we didn't want too much rotational flow of water, but we are going to get some rotational flow, and that's why we have to account for that using K. Okay, so we were able to pull the K pi in cubed part out because all the paddles are traveling at the same rotational speed, a number of turns per second, I guess. But their actual speed will vary according to their diameter, so the diameters now have to stay here in the parentheses as separate terms. Now we can do a little algebra and solve for the rotational speed cubed, or the rotational speed itself actually, and we move over to the top right of my page to do that. And then the rotational speed is going to be this after you did some algebra. And we've fleshed out here AP is 1/3 of the total paddle area, 10.8 meters squared divided by 3. And you ask yourself, wait, why is it 1/3 of the total paddle area? And the reason is because only 1/3 of the paddles are at D1, D2, or D3. Remember, this area is going to be multiplied times each paddle diameter to give us our denominator in this equation. So AP is that 1/3. So we get that 10.8 over 3. CD is the coefficient of drag. Now I know a lot of you haven't had fluids yet, so we're jumping a little bit ahead of game in your education, but if we go back to this slide, it simply tells us that this term that we call the drag coefficient depends on the length to width ratio. In our case, the length to width ratio is 20, so our coefficient of drag is 1.5. And does it make sense that the length to width ratio is 20? Well, our length is 3 meters, and our width is 0.15 meters, so yes, our length to width ratio is 20, and from slide 38 that we just looked at, our coefficient of drag is 1.5. Our density of water is 999.7 kilogram per meter cubed at 10 degrees Celsius that we looked up in a table. Of course, if we rounded to 1,000, that's still, it's only fourth decimal place or fourth significant figure off, so it may not have mattered too much, but that's what we're using. I will say that even though density doesn't change a lot, viscosity does change a lot with temperature, so you definitely have to use the temperature when you're calculating your viscosity. K is the 0.75 that we already discussed, and the diameter is 3, 2, and 1 meters, so we plug the numbers into that equation, and we have to do that 3 times, one for each compartment, because the G values were different, or the powers were different for each compartment. The other terms are going to be the same, I believe. Yes, all the other terms are going to be the same for each compartment, but the power is different for each compartment. So we do that 3 times, and we get that these in values in per seconds. So these are the rotational speeds, and then we can convert that to revolutions per minute. So this is revolutions per second essentially. This is revolutions per minute. 5.25, 2.85, and 1.80 for the respective compartments. Now here's just a check, does it make sense that compartment 1 has a faster speed than the others? That's the one that's going to have the most power, the most mixing. So yeah, it should have the faster speed. The later one is when we want a gentler mixing, so we're going to slow that one down. Okay. The 6th item to calculate was the speed of the motor with 1 to 4 turn down. Let's look at slide 38 of the chapter 3 supplement real quick. Here's the chapter 3 supplement, and let's maybe just zoom in on this picture a bit. And what we're seeing is this motor is turning sort of a little gearbox here, and there is one gear that we can see exposed, and then a bigger gear here, and this looks pretty close to this gear being 1/4 of the size of this gear. And the reason they do that is we need a pretty slow shaft speed, but motors don't like to travel too slow. And in fact, this gearbox is probably taking a motor that's traveling quite fast and slowing it down to turn this one, and then slowing it down even further, just like on your bike, fast in front. Well, on your bike it's big in front and little in back, but we're doing just the opposite. We have a fast motion here and we want a slower motion here. So this 1/4 to 1 turn down is why we're calculating this, and all we do is multiply the in values by 4. And so we get 21 RPM, 11.4 RPM, and 7.2 RPM, or in other words, this gear should be traveling at those faster RPMs to give us the slower revolution per minute at the top. So that's straightforward. And the last thing, step number 7, is calculating our tip speed. And tip speed is essentially what it sounds like. How fast is the very end of the paddle going? The circumference times the rotational speed is the tip speed. It's pi d times n, but in this case d that we have to calculate, it's going to be the diameter. It was 3. We used 3 for the diameter of the outer paddle, but the paddle width is 0.15 meters, and I guess we should specify here that the diameter of the outside paddle, we were really talking about the diameter at the midpoint of the paddle. So the tip is a little further out. It's half of 0.15 away. So we add that to the 3, and we have to multiply it times 2 because the total diameter is half the paddle plus the other half of the paddle. So I guess we could have done d1 times 1 paddle width, but this might help us see why we're doing it that way. And that total diameter is 3.15 meters, and when we plug that in, pi times this 3.15 meter diameter times the rotational speed for each compartment gives us the tip speeds for each compartment. And table 3.7 in your book recommends that this tip speed not be lower than 1.15 and not be higher than 1 meter per second. And now we say, okay, we're okay. And since our velocity gradient values worked, since our tip speed worked, since our cross-sectional area that we looked at a minute ago worked, we say this is a valid design and we can roll with it. That is how we design a flocculation chamber. Actually, the last point I'll make, why don't we want the tip speed to be too high? Well, it's all about breaking up those flocks. If the tip speed gets above 1 meter per second, then the flocks that are right here touching that tip, they're going to feel a very fast motion of a paddle coming by, and they're going to get broken apart, and we'll be destroying the thing that we're trying to create, which is a nice, fluffy, well-settleable flock. And so we ask ourselves now if we accomplished the goals of our problem. We did determine each of these items all the way down to the peripheral speed of the outside paddle blades in meter per second. So we are done.